Alright, we are talking in this little video about surface area. So the first thing we learned about related to this is how to find arc length, how to find the length of a curve, and we're going to use that information to be able to find surface area. So we've taken curves, we've rotated them around axes and ended up with volume, and we were calculating volume, but now we're talking about surface area, just the area on the surface, not the volume of how much it would contain inside. So let's say we have the curve y equals x squared, just regular old parabola. So it goes like this. Whoop, there's y equals x squared. Now I'm going to limit this section. Let's say we're only going to be interested in the section between where x is 0 and the square root of 2. We're only going to rotate part of this and look at part of that. So I'm giving you that information. I've got the equation of the curve, which we graphed. We're only looking at the section between where x is 0 and square root of 2. So here's where x is 0, square root of 2. I don't know, let's say it's right there. Okay, so I'm going to erase the other parts of the curve now that we're limiting what we're talking about here. Okay, there's that. And we're going to rotate this around the y-axis. Okay, so imagine having that little section of curve, and you're going to have to picture it. Picture rotating that thing around the axis, and it's going to get like a little mirror image thing. That was a horrible picture. But it's just basically going to be a little bowl, a short little bowl. And I want the surface area of that bowl. All right, so here's what you're going to do. You're going to use the same concept of cylindrical shells. You're going to have a bunch of different cylinders, which we already know that that's 2 pi RH. That's the area of a little surface area of a cylinder, and we're doing that along our whole region of the curve. So let's go ahead and fill in pieces that we know. I have my boundaries here, and generally they're going to give you the boundaries. So I'm interested in between 0 and square root of 2. Those are my boundaries. Let's talk about radius and height. I did not give myself much room in the picture. I tell you what I'm going to do. I'm going to blow up this picture, and I'm going to pretend like my scale at the bottom is really small. So let's just say that this is 0 and this is square root of 2 right here. Okay, so I've blown up that section so I can see it better. The cylinders that you're drawing, it's like little ribbons that you're making. All right, and so you might take a section of the curve from here to here, and you're going to make a little line for it, and you're going to rotate that little thing around. So imagine rotating it around. It's like a little ribbon being wrapped around into a perfect cylinder or circle. The height of that is the distance from this little line that I drew. That's arc length. So your height is always going to be arc length, which if you remember from the lesson before, arc length is the square root of 1 plus the derivative of the function. And my function at this time is in terms of y. So it's the derivative of y squared. That's the arc length, so I have that. Now we need to talk radius. Okay, let's look at the picture up here. All right, the radius, well, it depends on where I drew my little line, but it is a horizontal distance from the y-axis over to the curve. It's a horizontal distance, which for us, the horizontal line is x. So it's a distance of x. That's your radius. If you're rotating around the y-axis, your radius is going to be x. If you're rotating around the x-axis, you would have a vertical radius, so it would be y. All right? But there's some things that we'll talk about, and I'll show you an example later. The nice thing about this method is if you don't have the variables that you need, there's stuff you can change. But in this example, my boundaries are in terms of x's. I have an x as a radius, and when I do the derivative of y, it's going to be in terms of x's also. So that's your only job right now, is to make sure you have all the same variable. My boundaries are x's, I have an x for a radius, and my height is going to be in terms of x's also. All right, so I have to do this arc length thing, so off to the side, here's my y equals x squared. I have to do the derivative of y, which is 2x, and then I have to square it. So that gives me 4x squared. That's what I'm substituting into the equation. So I'm going from 0 to square root of 2. I'm going to pull out 2 pi. 2 pi x times 1 plus 4x squared to the 1/2 power. So instead of writing it as a radical, I'm going to go ahead and write it as that to the 1/2 power. All right, so we're going to do the u substitution thing because I need to integrate this. I need to find the antiderivative, but I have a product here. Okay, and there is no anti-product rule. So what you're hoping will happen is when you do u substitution, well, that's just what we're going to do. I don't even need to talk about it. So here's what you do. We have an issue because we have something in parentheses, and we want to make this simpler. So whatever's in parentheses, you're going to call that u. Okay, so u is equal to 1 plus 4x squared. The next step is you always take the derivative of your u. Well, the derivative of that is just 8x, and then we say dx. We don't really have a dx in this example, so we don't really have to worry about it much. I'm going to scoot everybody up. Stay with me. Now, my goal right now, I want to take all the x's out and replace them with u's. Okay, but you have to do it based on these rules right here. So I know that 1 plus 4x squared is equal to u. So I have u to the 1/2 power. Now the last thing I need to know is I need to know what is x in terms of u. So let's go to our definition here. We have du equals 8x. I need to know what x is, which means I got to get x by itself. So I have 1/8 du is equal to x. So instead of that x, I'm going to put 1/8 du. We always put du at the end because that's just what we do. Okay, that's what I have in my integral. And I can bring that 1/8 out, so I'm going to. So I have 2 pi, and now I have a 1/8 out there. So I took it out, so I'm going to scribble it out. That's so messy. Okay, so now to simplify, this 2 will cancel with this 8. I have pi over 4. And in my little integral here, I just have u to the 1/2 power. So that's an easy thing to do the antiderivative of. I add 1 to my exponent, I get u to the 3/2. I divide by the exponent, which means flip it and multiply. And then that's times my little pi over 4. So I can cancel a 2 here. So I have u to the 3/2 power over 6, and then that whole thing is times pi. So I'm done, really, but before I plug in my numbers, now remember I had boundaries? I had between square root of 2 and 0, so I have to get rid of the u now. It's time to put that back in. So u was equal to 1 plus 4x squared to the 3/2 power. All that's over 6, and then I have times my little pi. I'll tell you what, let's do, well, it's too late now. So my boundaries are square root of 2 and 0, so plug each of those in one at a time. Whoop. Okay, when I plug in square root of 2 into my little expression here, square root of 2 squared just gives me 2. So I have 2 times 4, which is 8. 1 plus 8 is 9. So I have 9 to the 3/2 power over 6. And I'm going to simplify that further, but that's what I get when I plug in square root of 2 into that expression. Subtract what you get when you plug in 0. So plug in 0 for my little x squared, and I get 1 to the 3/2 power over 6, which is just 1/6. 9 to the 3/2 power. The half on the bottom says square root. So I take the square root of 9, which is 3, and then I do 3 cubed, which is 27. So I get, when I subtract those, 26/6. And don't forget your little pi. The last thing you would want to do, of course, is reduce that because they're both even, so that's 13/3 pi. That's your surface area. That's it.